Okay, so today we'll finish this part 3 of chapter 2, which is on the symmetries and conservation law, right? So this is the last part of this chapter 2 on Lagrangian mechanics, and then we'll go to chapter 3, which is on central force problems. Okay. So last time I talked about how the conservation of momentum, of linear momentum, okay, so it's actually closely related to the so-called translational symmetry of your system, right? So, and today we'll talk about the conservation of angular momentum, okay, so and how it is closely related to the rotational symmetry of the system. Okay. So again, before getting there, a quick review on how do we get to the conservation of angular momentum, okay, from the Newton's law. Okay. So the Newton's law, right? So when we talk about the linear motion, right? So we have this dp dt equals f, right? And now what I'm writing down over here, so this the time derivative of this r cross p equals r cross f. Okay, so sometimes we call it the angular version, right? So of the Newton's second law, right? So, and this is nothing more than the original version of the Newton's second law. Okay, so I hope you remember that, right? So because if you actually try to expand the terms on the left hand side, right? So it would be something like this. Okay, so this is what we have on the left hand side. And the second term, if you look at the second term, right? So this is actually P cross V. Okay, so but P is m times V by itself, right? So the P cross V, of course, is just 0, right? So then the left hand side is r cross dp dt, and then the right hand side is r cross f, right? So you realize that it can be obtained by just taking the original version of the Newton's second law, and then you just do cross product with the r vector on both sides, right? So, okay. So now this left hand side with the time derivative of this r cross p. Okay, so hope you still remember that this is known as the angular momentum, right? And on the other hand, right, so on the right hand side, this r cross f is the torque. Okay. So, and now the angular momentum, right? So this r cross p, of course, this I'm just talking about this one particle system. Okay, and you can see that if the r cross p, right? So if I'm talking again about that this is being conserved, then what I mean really is that the time derivative, this ddt of this r cross p, or I call it L, to be 0. Right? And when does it happen? Right, it happens if you want this time derivative to be 0. That means the torque has to be 0. Right. So that is right. So the torque acting on the particle. Okay, so if it's 0, then the angular momentum is conserved. So this is what we have from Newton's second law, and this is what you have learned before. Okay. So here, right. So again, we are using another perspective. Okay, so to think about this. Okay. So, and I also believe that you have learned that the torque is 0, right? So it doesn't mean that the force is 0, right? So because as long as this one and this one are perpendicular, parallel to each other, right? So even if they both are non-zero, then your torque is still zero. Right? So one of the example, right, of course, is the so-called the central force, and this is actually the problem that we will exclusively study more, right? So in the next chapter, okay. So but anyway, so in this central force problem, where we have what we are thinking of is really this. You could think of this the Earth orbiting around a sun, right? So the sun, the Lagrangian, right? So it's written like this. So in this case, right? So you know that the potential energy of the Earth, right, is given by this minus GM m divided by r. Okay. And in this case, right, so what you can notice is that this Lagrangian itself, right, so what does it depend on? It depends on r dot theta dot and r, but not theta itself. Okay, so and because the potential, right, so only really depends on the distance between the two objects, okay, but not the angle between them. Okay. So if you take this Lagrangian, right, so and then if you go ahead and take this time derivative partial L partial theta, right, so of course you get that zero. Okay. So and because of that, right, so you will have this time, this p theta, okay, so which is the partial L partial theta dot to be conserved, right? So because from the Lagrange equation, right, so still remember that this partial L partial theta minus d dt partial L partial theta dot is zero. So this is the Lagrange equation, right? So and now that in this Lagrangian, right, so the partial L partial theta is zero, right? So that means that the time derivative of this partial L partial theta dot is zero. Okay. And remember this partial L partial theta dot is known as a generalized momentum. Okay. And in this case, in fact, it is this generalized momentum is the angular momentum of the particle. Okay. So you can actually go ahead and take partial L partial theta dot. You will exactly find that this is mr theta dot squared. So and now from this simple example, the thing that we can notice is that if L, the Lagrangian, right, so does not explicitly depends on the angular coordinate theta, right? So and then this generalized momentum, which is the angular momentum, is conserved. So if the Lagrangian does not depend on theta, what we say is that this system has rotational symmetry, right? So because that means if we just rotate the system by some angle or any angle, right? So the Lagrangian that you write down is still the same. Right? So that's what we mean by rotational symmetry here. Okay. So that's a simple example to illustrate this. But again, let's get to a more formal treatment, right? So again, we'll be considering the so-called the virtual displacement. Okay. So you still remember how we deal with the virtual displacement last time, right? So with the linear case, right? So last time when we talk about the virtual displacement, something happens like this, right? So suppose I have this particle which is originally moving like this, right? So virtual displacement means that you are going to translate it to another position. Okay, the virtual displacement I call delta r, right? So and you do that instantaneously, right? So remember that I told you to imagine that you are going to just be able to freeze the time, right? So and then you do the shift on this particle, right? So and then unfreeze it and then let the system evolve again, right? So that's the mental picture that I want you to have. So this time, right? So we are talking about also a virtual displacement, okay? But it's an angular virtual displacement. Okay. So what it really means is the following. Okay, if you now look at this picture over here, right? So again, I have a particle right here. Okay. So and this particle can have any velocity. Okay, it does not have to be. So I'm drawing this circle, right? So, but I'm not necessarily saying that this particle is doing a circular motion. Okay, so at a particular time, okay, so let's say it can take a velocity, for example, like this. Okay, this is okay. So now I'm just going to explain how an angular virtual displacement works, right? So that what happened is that you just imagine that you take a rotation axis, okay, so which is the center of this dashed line circle. So if you do a virtual angular displacement, okay, so what it really means is that you are, so I picked the axis already, right? So what you're doing is that you again you imagine that you freeze the system, right? So and then you try to rotate the entire system about this axis. Okay, so what happened is that the particle will be somewhere here now. Okay. And when you do that, okay, so you actually will also change the direction of the velocity vector. Okay, so if I draw another picture, this is, let's say I look at the system from the top. Okay, so originally the particle is right here. The velocity vector is pointing like this, let's say. And then after you do the angular virtual displacement, let's say the particle is over here. Then correspondingly, right? Okay, so the direction of your velocity vector, okay, so we'll also have to shift. It also have to change, not shift, change according to your angular displacement. Okay, so this is a difference. Okay, so between an angular virtual displacement and the linear virtual displacement I talked about. Okay, last time I shift this by some linear distance, and then the velocity doesn't change. This time, if you do an angular virtual displacement, okay, so you can see that the velocity vector has to adjust as well. Okay, so that's what happens. Okay, so now let me just take out the picture. So now I have some additional drawing on this paper, on this slide, right? So what you can see again, this is my rotation axis, the vertical one, right? So this is my rotation axis. And then this is, right? So this is the original position, right? So after the angular virtual displacement, it is somewhere here. Okay. So when we talk about angular virtual displacement, so I use this delta theta to label it. Okay. So delta theta, okay, by itself is a vector. Okay. So you can see that the direction of this delta theta is actually along the rotation axis. Okay. And then the length of this delta theta, okay, so we'll have to represent, okay, so the amount of this small angle delta theta. So if you So that then this arrow here, this R, is the original position vector of this particle. Okay, so I assume that this is the origin of my coordinate. So after the angular displacement, so this is the new position vector of the particle, which I call R plus delta R. Okay. So now the actual, right? So how much the particle has actually moved, right? So it's given by this small vector here, this delta R vector. Okay. And well, we do care about delta R, right? So I do care about how much it actually moved. Okay, so although originally I give you a delta theta. Okay, so and then but after that we also want to know what is the actual delta R. Okay. So in this picture, okay, so you'll be able to see that this delta R is actually equal to delta theta cross R. Okay, so let me remind you how it works. Okay, if you're familiar with cross product, this one should not be difficult for you, but anyway, let me just try to walk it through. So this length over here, what is this length over here? This length over here. So first of all, let me define this angle to be alpha. Okay. So then this green line over here, let me call this L. Okay. So this L would be, so I'm just talking about the length, right? So the length L would be the length of this R vector times sine alpha, right? So this is R sine alpha. Okay. And now what about the length of this delta R? Okay, the length of this delta R over here. Right, so you just imagine that this is an infinitesimally small triangle, right? So the length of this delta R would be this L times the delta theta, right? And which is of course the magnitude of R sine alpha and the magnitude of delta theta vector. And this one, right? So you can see that this is exactly the magnitude of delta theta cross R, right? Right, because the A cross B is equals to the magnitude of A times magnitude of B times the sine of angle between them. So you can see how the magnitude of this delta R is given by the magnitude of delta theta cross R. So what about the direction? Okay, does it sound right? Right. So and you can just use your right hand grid rule, right? So you can see that it, of course, it does, right? So the delta, right? So this delta theta, which is vertically up, right? So and then you take the cross product with this R, right? So then you just do something like this, right? So then that the vector is going that way, which is along this one. Okay, so then this is the key result. Okay, we'll use it again. Okay, delta R equals delta theta cross R. Okay. So an angular displacement, right? So will result in a linear displacement, right? So related by this. Okay, so I just write this down one more time. Okay, so and this just remind you again, right? So the angular virtual displacement, right? So unlike the case of linear virtual displacement, right? So it will actually change the velocity direction of your vector. Okay, and mathematically you can see how it works over here. So if I take the time derivatives of this linear virtual displacement due to your angular displacement, right? So then what you write down is this equation, right? So ddt delta R is this ddt delta theta cross R. So the delta theta itself, right? So by definition, this is an instantaneous operation, right? So this one does not really involve any time, right? However, the R itself may, right? So that's why this time derivative of this delta R, well, you can take this delta theta out, right? So this one is instantaneous, does not depend on time, but you still have this dr dt over here. Okay, so this is again an important equation that we'll use. Okay. So now, what did we do last time when we talk about the talk about testing whether the Lagrangian will depend on the virtual displacement, right? So we take some virtual displacement and we test whether the Lagrangian change or not. Right? So here we are trying to do the same thing, right? So by the formula of the total differential, right? So the delta L, right? So will have to be given by the sum of all these terms. Again, what is the difference between this case and the case last time? In the case in the last lecture, right? So I don't have the last three terms, right? So because in that case, I said it too many times already, but because in that case, right? So the virtual linear displacement does not give rise to the change in the x dot, y dot, and z dot. Okay. But here, not the case. Need to consider all six of them. Right? So, but again, this is nothing but just from the formula of the total differential, right? So, and then what we do next is to if I just take the Lagrange equation, right? So just write all this partial L partial coordinate as this d dt partial L partial velocity. So for the first three terms, okay. So see how I change this first three terms. Okay, so for the last three terms, I didn't do anything. And then remember, right? So this partial L partial x dot is actually your x component of the momentum, right? So y component of the momentum, z component of the momentum. Right? So, and this is also px, py, pz. Right? Just changing notations here, nothing else. Okay, then the next step, I'm just going to make the whole expression more compact. Okay, so the first three terms can be written as dp dt vector dot the delta r vector. Okay, so it's just nothing but this, right? So because delta r is delta x hat plus delta y hat plus delta z hat, right? And then your dp dt is your x hat dpx dt plus y hat dpy dt plus z hat dpz dt. Right, so that's why the dot product between these two vectors, right, are just right. So this one, and this one. Okay, so that's all you have. Okay. So similar for this one. Okay, so next, I'm going to. So the goal here is that I want to express at the end. I want to express everything in terms of something times the delta theta vector. Right. So then that's how I know if I apply some angular displacement delta theta, whether I have some non-zero delta L. Right. Okay. So that's why this delta R, I'm going to express it in terms of this delta theta, which is just the two equations that we have. So this equation and this equation. Right, so here I see delta R. I replace it by this delta theta cross R. And then I see this delta R dot replace it by this delta theta cross dr dt. Okay. So just repeat writing the same equation here again. And then next, what I do is try to make this delta theta, right? So as a overall common factor here. Right. So here I use this property here. Okay. So and now because I just want to delta theta dot with other something, right? So this is we're almost done. Okay, so now it's nice because we can express delta L in terms of some term, right? So with the dot product with this delta theta itself. Okay, and now this one should look pretty familiar for you. Okay, so this is exactly the time derivative of R cross P. Okay. So delta L equals delta theta dot the time derivative of the angular momentum. Okay. So now rotational symmetry, right? So what is the definition of rotational symmetry, right? So as I said, right, so it means that you rotate the system, right? So and then the Lagrangian does not change, right? So now that is right. So if I apply some virtual angular displacement delta theta, right? So whether delta L is 0 or not, okay. Right. So from here you can see that okay. So if I can say that delta L is 0, no matter what kind of delta theta you give me, if it is still 0, then that means that this second term over here by itself must be 0, right? So that is ddt of the angular momentum must be 0, and that is the conservation of angular momentum. Okay. So this is how rotational symmetry gives rise to the angular conservation of angular momentum. So one more, okay, so also a very important one, right? So it's the conservation of energy. Okay. And this time I'll show you how it is related to the so-called the time translational symmetry. Okay. So here we are not really shifting or twisting the system in space. Okay, so this is the time translational symmetry means that we see the system at some time, and then after some time we observe the system again. Okay, whether the Lagrangian is the same or not. Okay. So conservation of energy, or well, so we or I should say it more specifically, the conservation of a mechanical energy. Okay. So again, from Newtonian mechanics. Okay, so what did you learn over there? Okay. So we consider, right? So there's a particle moving along a path, any path S, and suppose there's a force acting on this particle when it's moving. Okay. And by definition, right? So the work done is given by this line integral of this f dot dr. And by Newton's second law, this f is this dv dt. Right? So then this is the integral that you have. So and now you apply. You just apply the chain rule, right? So this equation, this integral itself can be written as this form. Okay, so mv dot dv. Okay. And this one you know how to integrate, right? So this is v, this is also v. Okay. And if you do this integration, right, so you see that it is the 1/2 mvf square minus 1/2 mvi square. Okay, so vf means at the end of the path. Okay, so what is the velocity, right? So and then vi means the initial velocity of your particle. Right? So that is when it is at the starting point of the path. Right. So this is I think you have seen this, right? So this is the so-called the work kinetic energy theorem. So now, right, work done is equal to the difference in kinetic energy, right? So essentially. Now, if we consider the force, which is the so-called the conservative force, right? So the conservative force means that the force can be expressed as the gradient of a potential, right? So and that's most of the time that's what we deal with, right? So the spring system, right? So the gravitational system and or even the electrostatic system, right? So and in that case, right? So the work done, right? So which is the F dot dr can be written as this minus gradient U dr. And this is, right, so of course, we learned from the last semester, right? So this is the difference of the potential energy, okay? So between the end point and the starting point. Right? And remember that this one is the so-called path independent, if you still remember. So now that means I can relate, right? So the difference in potential energy with the difference in kinetic energy, okay? Right, so like this. Now rearrange the term, right? So and this one is exactly the initial total mechanical energy, right? And this one is the final total mechanical energy. So that's how you get to the conservation of mechanical energy, right? So with Newton's law. Okay, so now in the Lagrangian formulation. Okay. So I told you something that is known as the time translational symmetry, right? So but what do I really mean by that? Okay, so mathematically, okay, so that means that L does not explicitly depend on time. That is partial L, partial T to be 0. Okay. And in fact, in all the examples that we have encountered, partial L, partial T is always 0. Right? So if you remember, I always have this Lagrangian, right? 1/2 m, right? X dot square plus y dot square plus z dot square, and then minus the potential energy. Right? So whatever it is, right? 1/2 kx square or mg z or anything, but all the examples that we have, right? So the Lagrangian written like this, and it does not depend on time explicitly. So, but of course, one confusion here is that, but the x, y, z and x dot, y dot, z dot, they are all function of time, right? So yes, that's true, but that's what we really means here. Okay, so when I say that the Lagrangian depends on time explicitly, it really means that you cannot express the Lagrangian just in terms of your generalized coordinate. Right? So and you must add the time dependent term. So let me give you an example. Okay, so that might not be a very good one, but let's consider this. Okay, so if I have a mass spring system, okay, like this, just one dimensional, let's say, and you know that the Lagrangian is just 1/2 m x dot square minus 1/2 kx square, right? And in this case, I will say that this does not depend on time explicitly. Okay. However, suppose the mechanical property of this spring changes over time. So just imagine that you try to, let's say, heat up the spring, and such that the stiffness of the spring changes over time. Okay. So if if that's the case, right? So what you have is that, well, originally the spring constant itself is just a constant, right? So it depends on the material properties, but because you're heating it up, right? So changing the temperature, material property change over time, then what I can say is that this spring constant will become the function of time. Okay, so and in that case, right? So my L, well, I have to write it this way. Right. So this is a situation where I say that the mechanical system, okay, so the Lagrangian depends on time explicitly. Okay. So I do have a time here. Okay, so but anyway, you may be able to come up other situation, but this is one of the examples. Okay. So now let me consider this total derivative of this Lagrangian. Okay, so remember in the last semester, so I also talked about the total derivative and the partial derivative. Okay, so remember that by definition, the total derivative, right, is written like this. Okay, so and now, okay, so let me erase something. So so this line is nothing but just the basic definition of total derivative. That's it, right? Okay. So and why do I want to start from here? Because at the end, what I'm trying to show is that is the time derivative of the energy is zero, right? So that's conservation of energy. That is the end result I want to show is this. Okay. So, but I'm starting with this dLdt. So now from this step to this step, what I only change, what I only manipulate is this term, okay? Right, so this dq idt is qi dot, okay? And by Lagrange equation, this partial L partial qi is this ddt partial L partial qi dot. Okay. So then that's how I get to this term over here. Okay. And if you now look at the two groups of the term in the summation, right? So this one and this one can be further grouped together. Okay, so by using product rule. Okay, so this whole thing here can be written as ddt of this whole thing. Okay. That's product rule, nothing. Okay. And this partial L partial T is still standing alone by itself. Okay. So now I want to make this partial L partial T as the subject of the equation. Okay, so this partial L partial T will be equal to the ddt L minus this whole summation over here. Okay. So now I have this quantity over here, L minus something, okay, which I want to show that this is in fact closely related to the energy of the system. Okay. So this is nothing but repeating the last equation over here. And now I'm going to call that quantity that we just arrived at as the so-called Hamiltonian. Okay. So later in the semester, we'll have another entire chapter on the so-called Hamiltonian mechanics. Okay. But at this point, don't worry about that too much. I'm just saying that this quantity is called the Hamiltonian. Okay. This, by definition, is this one. Okay. So then if I call this Hamiltonian H, then this, I will say that this partial L partial T is equal to this minus dH dt. Okay. So what is this? Then I'm going to show that, okay, so this one is equals to the total energy of the system, the Hamiltonian. Okay. So I should remind you that in some cases, Hamiltonian might not be equal to the total energy of the system, but in the cases that I'm going to talk about, it is. Okay. So I'm going to show you that the sum of all these terms is equal to the 2 times the kinetic energy. Okay, let me make the common example, right? So suppose, right, so this L in Cartesian coordinate, right? So this Lagrangian is written like this. Okay, let me just focus on 2-dimensional case. Okay, so this is Lagrangian. The generic form of the Lagrangian looks like this. So then in this case, the summation of this Qi dot partial L partial Qi dot, what is it? Right, so in this case, my Qi are x and y, right? So that is x dot partial L partial x dot plus y dot partial L partial y dot, nothing but this. And this is equals to, if you just go ahead and 2 partial L partial x dot by yourself, you'll find that this is just m x dot. And similarly, this is m y dot. So what is this? This is just 2 times 1/2 m x dot square plus y dot square. Okay. So then you can see this quantity is 2 times the kinetic energy. So, and now this H would be this 2T by definition, this 2T minus L. And this L by itself, remember, is T minus U. So 2T minus T minus U is T plus U. And that is the total mechanical energy of the system. Okay. So here I show you a special case, right? So if we use Cartesian coordinates, right, so this quantity is indeed equal to the total energy of the system. Okay. So what about, let me also just try the polar coordinate, right? So if polar coordinates, then the Lagrangian is like this. Okay. And this time, right, so these terms, what is this? This would be R dot partial L partial R dot plus theta dot partial L partial theta dot. And if you go ahead and take the partial derivative by yourself, what you will see is R dot m R dot plus theta dot m R square theta dot. And that would again, right, so be equals to 1/2 m, okay, so times 2 R dot square plus R theta dot square. This is again equals to 2 times kinetic energy. Okay. So again, so that's why again in this expression over here, the Hamiltonian is again equals to the total energy of the system. Okay. So at least I hope now you're convinced that it doesn't depend on what kind of generalized coordinate we choose, right? So this Hamiltonian is the total energy of the system. Okay. And when I get to the chapter on the Hamiltonian, I will show you cases where this is not true. Okay. But for now, right, so you can just accept that. Okay. Right. So now, basically, I have I'm done with this, right? So because this minus dx dt, now I can really say that this is minus dE dt. Right, so the Hamiltonian energy. So that if partial L partial T is zero, right? So time translational symmetry, then I have this dE dt equals zero. That is to say that the total mechanical energy is conserved. So just a slide, last slide. Okay, so we have talked about three kinds of conservation laws, right? So momentum, angular momentum, energy. Okay, and in fact, these are the three special cases, and of course, the important cases of a more general theorem. Okay, known as the Noether's theorem. Okay. So we are not in this course. We are not really going to be talking about it in details. Okay, but what we can say, okay, within one sentence is that what is this theorem says is that if a system, okay, has a continuous symmetry property, okay, then there are corresponding quantities whose values are conserved, okay, in time. Okay. Right. So spatial translational symmetry gives the conservation of linear momentum. Right. So rotational symmetry gives the conservation of angular momentum, and the time translational symmetry will give the conservation of energy. Okay, so so we have finished this chapter 2 on Lagrangian mechanics. Okay, so and I think what you need, okay, of course, is to try to look at more example problems by yourself. Okay, so the homework 2, okay, will be all about the Lagrangian mechanics. Okay, and you need to submit that next Friday. Okay. So now let's take a break. Okay, let's take a break for maybe 15 minutes. Okay, so and then we'll come back to open a new chapter. Okay, start a new chapter. Okay, so now we'll start chapter 3. Okay, so this chapter 3 is about the so-called central force motion. Okay, so what we are essentially will be talking about is, as I also just mentioned, talk about is a planet, okay, orbiting around a star. Okay, so that type of motion. Okay, so and in this case, right, so we have a very special property, okay, for the force that we are going to deal with, which we call a central force. Okay. So the basic definition of a so-called central force field, okay, is given here, right? So what we are considering is a point particle, okay, of mass m, and then there is a force, okay, so which is always pointing at the origin of the coordinate. Okay, so in this case, I have this point O as the origin of the coordinate. So you can see that I define the position vector for this mass particle to be r again, and the force that is experienced, okay, so known as the central force, okay, so has the following two properties. Okay. One is that the force is always pointing towards the origin. Okay, you can see that I have this arrow, okay, so pointing towards the origin. So, and the other thing is that the magnitude, okay, so will only depend on the distance between the particle and point O. So that is, no matter whether it is over here, right? So, or if it is over here, okay. So if this distance is the same as this distance, the force, the magnitude of the force, okay, so will be the same. Okay. But one thing that changes is the direction of the force, right? So if the particle goes from here to here, right? So the direction of the force becomes this. Okay. So now, right? So mathematically, you could see that this kind of force, well, you only need to use the coordinate r, okay, so describe its magnitude, right? So, but not the theta coordinate. So that's central force, right? So because for example, right, so the gravitational force will be this, right? This is something that you have seen before, right? No theta dependence, okay, and this direction always given by this r hat vector. And of course, we are going to consider the conservative force. Okay. So it can be always written as the gradient of some potential function. So just now I talked about rotation, symmetry, and angular momentum, right? So and this example, right? So of course it's exactly an important example that has the rotational symmetry. Okay. So again, right? So in this picture, I'm making it looks like the particle is moving along a circle. Okay. So but as we will see later, so it does not necessarily be the case. Okay, could be other shape. Okay, but the rotational symmetry is always there. Okay, with central force doesn't really happen only when the particles move along a circle. So in this case, right, so we do have angular momentum being conserved. Okay. So this is an important property that can help us to simplify the problem. Okay. So first of all, right, so when we talk about conservation of momentum, right, so we mostly care about the magnitude of the angular momentum. But however, there's another important property that is the direction of the angular momentum. But that one is also being conserved, right? So if when I say that angular momentum is conserved, I will have to say that both the magnitude and the direction is being constant as a function of time. So what is the significance of that? Right. So if I have this picture over here, right? So if I have this R and P, so the R cross P would give me a vector L, right? So which is perpendicular to both R and P, right? So that is the angular momentum vector. Right? So then when I say that this L is conserved, right? So that means this L, right? So has always have to be pointing in a constant direction. And that means this R and P will always have to be staying on a particular flat plane, right? So if not, right, so then this direction of the L will be different, and that violates the conservation of angular momentum. So therefore, when we talk about this central force problem, right, so even without start doing the equations, okay, so we know that the trajectory or the orbit of the particle will always be staying on a flat plane. Okay. And that makes the problem easier, right? So because initially, so we are really starting with a three-dimensional problem, right? So, but now we know that it's actually effectively a two-dimensional problem. Okay. Once we know what plane it is on, okay, then it's always is on that plane. So then just two-dimensional problem, and with this kind of central force, okay, we immediately know that this is convenient to use polar coordinate system. And the Lagrangian written like this. So equation of motion, right? So if I go ahead to have this equation, Lagrange equation written down, then again I have these two equations over here. Alternatively, right? So even if you don't pretend that you don't know Lagrange equation, just from Newton's second law, you should be able to obtain these two equations over here. Okay, so and in the last chapter, so I reminded you that in this chapter, polar coordinate will become very important, as that's the only coordinate system that we are going to use in this chapter. Okay, so if you're still not familiar with that, okay, so should really go home and revise on do revision on that part. Okay. So now, right, so the first one is the partial u partial r, right? So it's the force in the so-called the radial direction. So and then the second one, right? So it's the force in the transverse direction. But because of the fact that I told you that this is a central force problem, right? So that's why I only have the radial part of the force. So that is when the polar coordinate becomes convenient to use, right? So when we only have the radial part of the force. Okay, so now here I'm just rewriting the equations again. Right. So now I have made use of the fact that the direction of the angular momentum being conserved, right? So and another thing is that the magnitude of the angular momentum also conserved. Okay. So that is this quantity, this here, mr squared theta dot, right? It's being a constant, which I'll call L. Okay. I'll call L. Okay. And how big is this L? Right? It really depends on the initial condition of your problem, right? So you need to initially, if you give me some distance and some initial value of theta dot, then I can calculate this L, and this L is remain constant over time. Okay. So this will be important, right? So because what you see in the later is that it relates the R and the theta dot, right? So what we are going to do next is to find out R as a function of theta. Okay, but that's the later part. Okay. But as for the conservation of angular momentum, okay, so let me say one more thing, and this is something that I believe that you have heard of, which is the Kepler's law. Okay. So what we really saying here is the following. Okay, so this solid line, this solid curve is suppose is the trajectory of the particle. Okay, so and the force comes from pointing to the origin. So suppose it's moving like this. So at some time t is over here, and then at some later time t plus delta t, dt is over here. Okay. So that is right. So this is the position vector at t. Position vector at t, and then position vector at t plus dt. Right. So the position vector, well, will sweep out an area dA. Right. So what I really mean is the region that it has sweep across. Okay, so this is the area. Okay. So what is this area over here? Okay, again, you have to imagine that this t plus delta, this delta dt is very small. Okay, so then in that case, let me just focus on this part. Okay. And this part I will ignore. So this red part is a very, very narrow triangle, right? And that you could see that this is 1/2 times this width r d theta, okay, times r. So then that's 1/2 r square d theta. And as for this part, right? So this part, because this I have the r d theta here, right? So and this one is also very tiny. Okay, so then it's this one I can ignore. It's just a tiny number times a tiny number over here. So then this area is just given by this. So now I'm going to define one thing known as the aerial velocity of the particle. Okay. So it's given by this dA dt. Okay. So that is within what is the area that is swept out, okay, so per unit time. So and this dA dt, right, so would be given by this, okay, 1/2 r square d theta dt. And remember, right, so this r square theta dot, right, so this mr square theta dot by itself is the angular momentum, a constant. So that's why this dA dt can be written as this L divided by 2m, right? And that is a constant, right? So due to conservation of momentum. Okay. So this constant aerial velocity, so these properties, okay, so was actually first discovered by Kepler, right? So he got this law according to observational data, right? So but although, right, so it's not due to using the argument of conservation of angular momentum. Okay. And this is known as the Kepler's second law. Okay. And also notice that of course when Kepler did it, right, so he's looking at the planetary motion, and that kind of planetary motion is the 1/r square force, right? So but in principle, right, so it does not have to be 1/r square force, okay, so to have this nice property, right? So as long as it's a central force, then this property should hold. Okay. Okay, so we do have the equation for motion, right? So then basically what we have in this chapter really is to understand the properties of the motion of this particle, right? So in principle, right, so that is what we need to do is to obtain, right, so r as a function of time and theta as a function of time. Okay. So but in the following, okay, so we'll just mainly worry about the shape of the orbit. Okay, so then instead of solving the r as a function of time and theta as a function of time individually, okay, so we're mostly interested in solving r as a function of theta. Okay. That's sufficient for us to draw the shape of the orbit. Okay. So then let's try to do that. Right. So we have these two equations. Right. So then what follows are just mathematical skills. Okay. So we are going to do a substitution, okay, which is u equals 1/r. Okay. Right. The strategy is that we are going to we want to somehow simplify this differential equation. So you can see that if I just start from here, they are rather complicated, right? So because the variable r and the variable theta, they are coupled together, right? So at the end of the day, you want to have an equation, okay, so that just contains one of the variable, right? And then you are so that we can solve that. Okay. So the trick is to use, right? So the U equals 1 over R. Okay. And if you do that, and then you take the chain rule. Okay, so let me just focus on the first line. Okay, so this DUD theta. So what is this DUD theta? DUD theta, if I use chain rule, is du dr d theta. Okay. And this du dr is d dr 1 over r. And of course, this is minus 1 over r squared dr d theta. Okay. So that's why I have this term over here. Okay, this one is from here. Okay. And then next, this drd theta, I applied chain rule one more time. Okay, so this one becomes drdt dt d theta. Okay. And now we'll be using the same strategy more than one time. Is that whenever we see this d theta dt, which is a theta dot, okay, we will replace it by L divided by mr squared. Right. So remember, this one is from conservation of angular momentum. Right? So then here I have this dt d theta, which is 1 divided by theta dot. Then I replace it by this. So give me this. Okay. Then that is du d theta at the end is just minus m divided by L times r dot. Okay. So now if I similarly, right, so taking the second order derivative, you should be able to get to this one over here. Okay. So, and I'm just going to use r double dot as the subject. Okay, so then that gives this over here. Okay. So now if I substitute this star, okay, and this equation to this, where's my equation 3? So then I will be able to get this d square u d theta square plus u, okay, equals to this over here. Okay. So now this one you can see that I only have one variable, which is the u. Okay, and this is no longer a differential equation with respect to time. Okay, so this is the differential equation with respect to theta. And remember, this u is actually 1 over r, right? So then I got this. Okay. So this one still looks a bit complicated to you, maybe, but you can see that this is a second order linear ODE. Okay, so but of course this is inhomogeneous. Okay, so you just consider the right hand side to be 0. Okay, you actually immediately know how to solve this. Right. So now I just have the right hand side, right? So which really may make the problem more difficult, right? So but it has to depends on how complicated, right? So this term is. So if this one, right? So give me some particular easy form, then this equation is easy to solve. Okay. So for example, if the f of r is proportional to 1 over r squared. Okay. So then what do we have for the right hand side? So the right hand side over here is just a constant. Right. then actually that one you can solve, right? So you know how to solve this inhomogeneous differential equation, right? So with this constant on the right hand side. Right? And the other case, right? So if I have f over r is proportional to 1 over r cubed. So then you can see that the right hand side is also proportional to 1 over r. So this is case 1, this is case 2. So if this is also proportional to 1 over r, you can just really put the whole thing to the left hand side, right? So because this is also 1 over r term. So then you can see that, right? So at least, right? So in these two cases, right, so this one is actually quite manageable. And in fact, you know which one we do care about a lot, right? In fact it's the 1 over r squared, right? So because this is what we have for the gravitational force. Okay. So, and in fact, right, so this equation is also useful for something else. Okay, is that if I do it the other way, right? So suppose I don't know the form of this force, okay, but if I know the shape of the trajectory, so r as a function of theta, then I can tell you the f over r. Okay, you just need to compute these two terms together. Right. So one example. So if I give you this r as a function of theta given by this term, right? So what it looks like a spiral. Okay. So then we can show that the force is actually the 1 over r cubed. The 1 over r cubed. So how do we show that? Right. So we are just going to use this equation we just derived. Okay. So the 1 over r would be equal to, right from here, 1 over r would be equal to k e minus beta theta. And then if I just go ahead and take the derivative, right, d1 over r d theta, what is that? That's actually easy to do because it's just an exponential function, right? So that would be minus k beta e minus beta theta. Right, so taking the derivative one more time. Like this. So and now the left hand side, right? So the total what I have in total, right? The two terms added together would be just this term at this term. Right? So and you'll be able to find that this is k e minus beta theta times beta squared plus 1. And this whole thing is equal to 1 over r beta squared plus 1. And what about the right hand side? Right, so this one has to be equal to the right hand side, which is equals to this minus m r squared l squared f times r. And that's why this f as a function of r is given by minus l squared 1 plus beta squared divided by m r cubed. So you can see that actually, if we have this 1 over r cubed dependence of the force, right? So the trajectory is like a spiral, like this. Right. So as I said, right. So we can do it the other way around, right? So if I, let's say, right? So here I just tell you, if I just tell you f of r is given by minus k divided by r cubed, right? So and this time I want to find r as a function of theta. Okay. So how do I do that, right? So then if I substitute this f of r to this equation over here, right? So you'll be able to see that the differential equation is like this. Like this, right? And this is just a second order homogeneous linear differential equation, right? So and you immediately see that the solution exponential function. Okay, so in principle, right? So if you know this equation, and if you just plug in the 1 over r square over here, okay, you will be able to solve for the orbit, okay, for a planet orbiting around a star, okay. But here I will also tell you the other method, which is more commonly seen in your textbook, okay. So is that I'm going to start from considering the energy, okay. So the energy of the particle again, right? So this is another conserved quantity, right? So the total energy, right, is the kinetic energy plus potential energy. And again, we use a strategy that whenever I see the theta dot, right, so I just replace it by this L divided by mr squared, right? So then the total energy just depends on R and R dot. Okay. So and what I do next is that I'm going to make R dot as the subject, okay. So and then I put everything else to the right hand side, okay, and then take the square root. Okay. So because of taking the square root, okay, so I will have to have this plus or minus up front, okay. So but anyway, this is square root of some big term. Okay. And then again, here we are not really going to care about, at least here, I'm not going to care about this r as a function of time, right? So I'm going to just again work on r as a function of theta. Okay. And now we call that again one more chain rule over here, right? So this CRD theta is actually given by this r dot divided by theta dot. Okay. And that would be this whole thing divided by theta dot. And I see theta dot again, I replace it by this L divided by mr squared. Okay. So now this DRD theta is given by this whole thing, which only depends on R anyway. So then this differential equation can be solved by what? Just separation of variable. Right. So just put everything on the right hand side. Okay. So this kind of this integral over here. Okay. So now here, right? So u of r, I didn't say what it is, but again, as I said, we care about the inverse square law, right? So this is 1 over r squared. Okay, and in that case, that means the u is minus k divided by r. Okay. I hope you remember how to obtain this u, right? So from this f, right? So I think you have learned about that. Just taking an integral, right? So then I actually plug in this form of u I want in this integral over here. So then what really follows are the mathematical skills. Okay, so it is a coincidence that we again, okay, use the same substitution. Okay, u equals 1 over r. So and if that, so I convert the entire integral into this form. So, and next, the strategy over here is that, so if you see this integral, what we want eventually is to try to make the denominator to a form that looks like this. A form that looks like this. Okay. So I have this u here, I have this u square here, but doing the completing the square, okay, so it's not difficult to see that this one can be somehow converted to this form, and this one we know how to do the integral. So this one is the standard one. Okay. So then what I do below here, as you can see that I'm just completing the square. Okay, basically completing the square. Okay, you can see that this is a constant. Okay, and this is the u minus something over here, minus some constant. Okay. So, okay. Now, further simplification. Okay, so this one, I just give this du divided by the square root of 1 minus this whole term. Right? So the variable is this u over here. So from this point to all this, okay, so I believe you can just try to work it out one time by yourself. Okay, just basically, as I said, just taking common factors and completing the square. Okay, so from here to here, that's all it's about. And you can see that I'm making some new variables here. So this alpha is denoting this L squared divided by mk. Okay. And this epsilon, okay, is this one. Okay. It might take a bit time, but just completing the square. Try by yourself. So integrating this actually is this arc cosine function. Okay. So, and because of the fact that we are doing an indefinite integral, right? So then I will have to add some arbitrary constant behind, which let me just call that theta naught. Okay. So now if I just move this theta naught, right, so to the left hand side, and then taking the cosine of both sides. Okay, so then this is what I got. Okay, one small thing here is that the plus minus sign here disappear. Okay, but it is just because of the fact that cosine x equals cosine minus x, right? So that's why you can absorb the plus or minus sign. Okay. So, but at the end, right? So this is the shape of the orbit that we'll get, right? Just one more step is that I just put this u back to 1 over r. Okay. Okay, so this is an orbit. Okay, r as a function of theta. Right, so that's what we want over here. Okay. So, but what is this? Okay, so what is the shape of this thing? Okay, so which we'll talk about very soon. Okay, so but one small remark here is that this theta naught, right? So this theta naught, as I said, is the arbitrary constant, right? So given by the integration, right? So and it depends on the initial condition, right? But one thing I want to tell you is this theta naught itself does not really change the shape of the orbit. Okay, actually, it will change the orientation of the orbit. Okay. So look at this picture over here. Okay. In general, if I have this r as a written as a function f theta, and if I have another which is written as f theta minus theta naught. Okay. So these two actually have the same shape. Okay. The difference is just that one of them is rotated by an angle theta naught. So, and because of that, right, so I'm just going to drop the theta naught. Right? So because it does not really affect us to studying the shape of the orbit. Okay, just for simplicity, let me just put this theta naught to 0. Okay. It can be always achievable by choosing some appropriate initial condition. Right? Okay, so one more thing here. So this is I've talked about this one already actually, right? So is that if you put this 1/r r square for the force, right? So the right hand side will become a constant, right? So the right hand side is just a constant. Right? If you forget about this method itself, right? If you just start with this equation, which I derived earlier, right? Just solving this equation itself, well, should also let you find out 1/r is some kind of function of theta. Right? And this, you might verify that will give you the same result as this one. But anyways, this is the key equation here now. Okay, so we'll be studying the properties of this equation of orbits. Okay. So let me tell you that in polar coordinate, okay, so this form of equation is actually the equation of a conic section. Okay. And the conic section has 4 different kinds of shape, right? Hyperbola, parabola, ellipse, and circle. So I'm sure that maybe in polar coordinate you are not that familiar with, but in Cartesian coordinates, I'm sure that you know that for hyperbola, it's written like this. And for parabola, it's like this. And ellipse, like this. And circle, right? Like this. Okay. So here we can do a quick exercise on showing that this is equivalent to all this. Okay, so that's not difficult to do, right? So just a conversion from the polar coordinate, right? So back to the Cartesian coordinate. So the transformation, right? So what we have is, of course, x equals r cosine theta, and y equals r sine theta, right? So that's the transformation that we need. So if I look at this equation over here, then what I have is alpha equals r plus epsilon r cosine theta. Right, I just take the r to the right hand side. And this r cosine theta is x, right? So now if I change the subject, then I have this r squared equals alpha minus epsilon x squared. I'm taking the square on both sides. Okay, so then that's why I can rewrite this r squared as x squared plus y squared. And if I just expand the other side, right, so that would be alpha squared minus 2 alpha epsilon x plus epsilon squared x squared. So you can see that I have this x squared and y squared term coming out. I also have some x, but this one, okay, I can just further simplify it as this. Okay, you can, I have skipped the steps, but you can try by yourself if you want. Right. So this one, right? So looks like an ellipse, right? So now, what is the difference between this one and this one? So here, instead of x squared, I have x plus something squared. But what it really means is just that a shift of the center of the ellipse, right? So that means the center, this ellipse is centered at minus epsilon alpha divided by 1 minus epsilon square and 0. So now I do have some picture at the end, but I think, okay, I should stop soon. But here I just plot some pictures for you. Okay, so just to show you if I am going to take this equation, okay, so and then tune the parameters, okay, how the shape of the ellipse will change it. So as I said, okay, I'll talk about this again next, okay, but you can look at them just for now. Is that here, right? So I told you that in the polar coordinates, if I write this kind of equation, right, so it can be an ellipse, but it won't be centered at 0, right? So and here that's what you exactly see. Okay, so this is the origin of the coordinate. Okay, but you can see that the ellipse is not centered at here. Okay. Okay, so then we'll continue next time. Okay, so we'll see how the force, okay, will give rise to all these objects. Okay. And at what conditions will we get an ellipse, and what condition we will get parabola, hyperbola, or circle?